This is one of the best parts of grad school in engineering. We were really just scratching the surface earlier, but you'll see the way we've learned so far, this is going to be a piece of cake for you. Just the way we will present it, we'll explain it. We're just augmenting your knowledge one step at a time. So compare yourself today to yourself at the beginning of the course. I hope you learned something. I hope phi n plus 1 is greater than phi n. In other words, you grew with knowledge. The material I will present for the rest of the semester, most of it will likely be novel to you unless you've taken a course in advanced transport or mechanics. Again, so continuing with the tuning forks joke. Welcome, you can come in. No? Okay, so as I said, if differential equations are the tuning forks of math, then PDEs are the tuning forks of differential equations. And the way we will learn about partial differential equations is through conservation laws. So not just any type of partial differential equation, but actually the most useful type of partial differential equation, and you'll see what they are. And they are based and they come from what we call conservation laws. People think of conservation laws or balance laws, they call them, and get confused like is velocity conserved? Is kinetic energy conserved? Is total energy conserved? Is the pressure conserved? What is conserved? What is conservation? How do we express these conservations idea? Why are they like that? Why is a quantity conserved but a quantity is not conserved? Can you develop an equation for an unconserved quantity, and why you shouldn't develop, or you might have to sometimes? And so we'll answer all of these questions for you because I know you think about them every night. They keep you up at night. I'm joking. Hopefully they will keep you up at night as you become a PhD. All right, the basis of conservation is conservation are the basis of engineering science. And there's three critical conservation principles. So I interchangeably use the word law and principle. To be clear, the conservation law is the equation expressing a conservation principle. So I write an equation, I tell you this is the conservation law for the conservation of mass. So by law, I mean the differential equation that expresses the conservation principle. But you'll see that mixed up here and there, so we don't confuse that moving forward. There are three conservation principles that we base everything on in chemical engineering and engineering science. And in chemical engineering, things are transported. You have a medium, a fluid, that is taking reactants together, mixing them. They're bringing bacteria, bringing a therapeutic, right? So there's a fluid that is moving information around, and the conservation principle is going to tell us how we develop the equation for how that fluid is moving, how the solute or the reactants or the bacteria or whatever you're moving with that fluid is going to move around according to these basic principles: conservation of mass, conservation of linear momentum, or momentum in general, because we have conservation of angular momentum as well. We can develop an equation for that. We don't have to talk about it. Conservation of total energy. That's the first law of thermodynamics. We can talk about entropy, but these are the three most important conservation principles for which we will develop conservation laws or differential equations. Okay? You will need to master these principles and their corresponding equations. You're going to see them again with Professor Sutherland and Professor Yachow next semester, but they're going to be applied to non-pure fluids. So you will have multi-species reactions going on. You know, things will change a little bit. So if you master things for the pure fluid, you can hit the ground running next semester. We are primarily concerned with how information is being passed around. By information, I mean a general term. This could be velocity is information, pressure is information, temperature is information, everything is information. You are information. We all are. Information is the tuning fork of everything. Okay, so information is anything that can be communicated. Okay, knowledge, quantities, these are all information. Okay, we will consider a general fluid because things move with the fluid. You need a fluid to move things around. We will consider a general fluid flow. Looks like this. Just kind of some, I put here what we call streamlines, and things are circulating in it. So this could be the flow in a pipe or a chimney or a stirred reactor. And we will consider a few properties for this fluid. The most important quantity, I wouldn't call it a property, the most important quantity is the velocity field. So at every point in this fluid flow, you have a velocity vector. And that consists of three components. So we talked about vector fields. So there's a field of vectors that correspond to the velocity. These determine the speed at which the fluid is moving in all three directions at any point r in space and in time. We will also consider a few additional properties of the material, of the fluid: density, viscosity, pressure, temperature or energy, species, or a general tracer phi. Phi is our dummy variable for a tracer. Think of ink, just to help you see things. Okay, so sometimes I want to see how the fluid flow. I look at water, I'm like, it just looks clean to me. But if I want to see how the velocity field is shearing the material, put some ink along it, and you'll see how, when you're close to the boundary, the flow is slow, and then when you're away the boundary, the ink is going to move faster. Right? So ink is a tracer, doesn't react with the fluid, doesn't affect the fluid flow, is just being moved by the fluid. Okay? Or a tracer could be a viral concentration. The air is moving the virus around. Okay? That's what you do when you go on Southwest. You sit and start sneezing. Nobody sits next to you. You can sleep on the aisle. Okay? All right. So these are all fields. So when I say density, this is a density field that could change in space and time, unless otherwise noted, unless I tell you density is constant. Viscosity, the same way. We'll talk more about viscosity when we hit fluid flow. But viscosity is like diffusion. It's a property of the fluid that could change in space and time. It could be dependent on the temperature too. So these are all valid. Or it can be constant. Okay? So I just here picked the fundamental properties: density, pressure, and velocity. But then you ask the question, before we even develop equations, we need to figure out what do we mean by the velocity or the pressure at a point? How can we define this? Is this the velocity of a single water molecule if you're looking at water? Can you does a molecule, have you seen a water molecule? It's like going crazy like this, right? Can you define a velocity for that? Does it have a pressure? Does it have a temperature? No. Okay, so in fact, we cannot define these properties or these fields at a point, because where do you go down? Do you stop at the molecular level? Do you stop at the atomic level? There's no atomic speed. Right? So there's a point below which we cannot define quantities that we see macroscopically and that we measure. We cannot define those. We are looking at macroscopic things, right? We're not looking at molecular dynamics calculations or studies, right? We're above that scale. So there is a scale at which we can define these properties, below which it's going to be impossible to define this. So in fact, we can't define any of these at a point. So what do we mean by point? And this is strict. So it's not a mathematical point anymore. There's a physics point. What's a point in physics? Is that in the vicinity of the mathematical point in space, in the vicinity of that, we're going to take a volume, draw a volume, a sphere, and calculate the average of all motions in that sphere, and say this is our point. So the density in that sphere would be the density at that point. The speed, the average speed of all molecular collisions and whatever is going on in that volume is going to be the speed at that point, the velocity, the pressure, the temperature, etc. But we cannot define it at a single point. It's an average within the vicinity of that point. Okay? So you're taking this point and you're drawing a volume. Now, how small can you go for this delta V star volume around this mathematical point, right? So this volume contains molecules of the fluid, and how small can you go? How big can you go, right? Obviously, you want to go to the smallest possible volume you can, because you want to be closer to what we mean by a mathematical point, truly. So how do we do this? Suppose, I'm just going to give you an actual, like a realistic situation, just to understand how this works. Suppose you are measuring the density of some fluid in a large system, say air in the atmosphere. Okay, so the density of air changes. The density of the air is higher, closer to the ground, than as you go up in the atmosphere, right? Same with seawater. The density of seawater, we say water is incompressible. Well, the density of seawater changes by as much as 3% as you go down deep in the ocean. So suppose that you have a fluid like this, you know, this huge distances here. I don't know, you're on Jupiter. There's like incredible pressures that are crushing the atmosphere, okay? And at this point, you have a density of 1300, and this on this constant line, the isobar, we call it. It's a constant density line. The density, anywhere at this point, the density is 1300, suppose. And here it's 1200, here it's 1100, here it's 1000. And then you're going to pick a point here, and you're going to start collecting volumes from that liquid. You go and grab a 1 cubic nanometers of water, okay? And then you go and measure somehow all the molecular weights, etc., and figure out the density. And then you continue expanding that volume all the way until it reaches probably across 2 or 3 of these different lines. So what do you think is going to happen? So here I'm plotting the density that we will measure versus this representative volume. So let's start with 2 molecules, right? And then start with a very small volume that contains 2 molecules. The next volume might contain 20 molecules. The next volume might contain 1 molecule, right? Because as it's very small, you're within, you know, the free path of these molecules being apart. So what do you think is going to happen? What happens in actuality, as your volumes are really small, you are hitting what we call microscopic uncertainty. One volume has a million molecules, the other volume has only 10. Because molecules are moving all around, you're still so small, your volumes are so small, you're randomly sampling, you're not consistently hitting a consistent number of molecules. And then the density, if you measure that in those volumes, this is exaggerated obviously, you're gonna see this oscillation. Sometimes you're gonna be above 1200, sometimes below, etc. And as you keep increasing your volume, you're gonna reach a point where you're consistently sampling about the same average number of molecules that have a correct density representation of the flow, of the fluid. But then what happens when your volumes become very large? So take the air for example. If I grab this volume, density is constant. But if I grab a volume that's 2 kilometers in diameter, I'm gonna hit many layers of density, right? So the average is not going to be the density here or the density up in the atmosphere. It's going to be somewhere in between, right? So you start seeing oscillations also at large volumes because you're hitting larger and smaller densities, right? So you can't go too large and you cannot go too small. This is called macroscopic uncertainty. There is a volume at standard air and pressure conditions that's about 10 to the minus 9 cubic millimeters. This was an experiment done. And you know that volume is below which you have the microscopic uncertainty, above which you have a good range of volumes where the density remains constant. So we take this volume as our representative of a point. Okay, about 10 to the minus 9 cubic millimeters. Okay? It's small. It contains a few hundred million molecules of air. So this is for air. But this is essentially when we say things are valid at a point, remember, on average, they're valid at this volume, okay? Now, we tend to forget that once we go to the differential equations and treat everything as a pure continuum in the mathematical sense. But physically, this is your continuum. If you go below, your equations that we talked about, we're going to talk about, like the fluid flow equations, they're not valid for molecules. If you go up in outer space and you have one molecule every mile, Navier-Stokes equations don't work there. Okay? So you have to have enough material packed together that that those equations work at. So keep that in mind. Another way to measure, to assess whether your system can be treated as a continuum or not, it depends on relative scales. So, and the idea is to define a ratio of two characteristic scales, length scales in the system. The first one is the mean free path. Anyone from chemistry or can tell us what the mean free path is? On average, yep. So the mean free path is the average distance that a molecule has to travel before it encounters another molecule. So it kind of essentially tells you how spread are the molecules are in a given fluid or gas at certain temperature and pressure, how far they're separated apart. So it gives you an average distance that's free between, that's empty between two molecules. And then also you have a characteristic length scale of a system. So for example, a nanochannel, it's probably the channel's height. A pipe flow, it's the channel diameter. That's your characteristic length scale. The example we're going to do next is this mug, the thermos, right? So the in this mug, there's two walls out here, right, separated by this distance. That's my characteristic length scale. And there's a vacuum in there. Okay? So the vacuum means my mean free path is pretty large, right, because I took out as many molecules as I can. So now the average distance between two, for a molecule to hit another molecule is going to be large than standard air. But also there's the scale of the thickness of these two walls, the distance between those two walls, right? So if you take the ratio of that mean free path to the characteristic length scale, it defines a dimensionless number called the Knudsen number, given by this Kn. It's a dimensionless quantity. It doesn't have units or anything like that. And then you say, if my Knudsen number is less than 1 or much less than 1, then we declare a continuum. What this means is that the mean free path is much smaller than your characteristic length scale. Okay, there's a law. It means that there's going to be a lot of molecules in that characteristic length scales that you're dealing with, and therefore, most likely, you are in a continuum. So you take a nanochannel, for example. Lambda, the mean free path is about 0.1 nanometers, but the length of the nanochannel is about 10 nanometers. Okay, so 0.1 nanometer distance versus 10 nanometers, that's, if you take that ratio, it's 0.01, much less than 1. So there's going to be enough molecules in those 10 nanometers that you have a continuum. Okay? Then if you go and take, on average, a volume, it's going to be sufficient enough that you can declare a continuum. The other one is this thermos cup. The mean free path is about 1 millimeter, but also my distance, because I vacuumed all the molecules, right, of the air, the next time whatever is left from the air in that gap, whatever is left, the next distance is going to encounter a molecule at is about 1 millimeters away. But also the scale of the channel of the distance between the gap is also 1 millimeter. So there's not enough of these molecules to declare a continuum. In this case, the Knudsen number is about 1, and we cannot apply whatever we're going to do next to study how the air moves inside the gap here. Okay? Same thing for double glazed windows, double paned windows, right? You have a vacuum in between. This is not a continuum inside them, unless your kid throws a rock at it and breaks it, right? So, okay, then like I asked my kid, what are you doing? I'm making continuum, Dad. So, okay, you can laugh. Daddy jokes. I have a couple more years before my kids grow up and be embarrassed by me. So, okay, we will derive the conservation equations. Thank you. We will derive the conservation equations in two ways. So again, these are the equations are the conservation laws. And when I say conservation law, I'm referring to the differential equation. We'll derive them in two ways. The first method is going to be in this lecture and the next lecture. And it's based on the idea of a simple accounting principle on a volume in space. We're going to take a volume in space and we're going to do simple accounting. Whatever is coming in needs to be balanced by whatever is leaving plus whatever being generated. Now that principle, it's so obvious to you because you learned it, you've been hearing about it throughout engineering, but it wasn't obvious 200 years ago, right? It took time to figure this out and think about it. So that's called the balanced approach to conservation laws. It's an okay approach, but there's some mystery in it, because when I come and tell you, okay, this is the diffusive flux, how the heck did you figure out the diffusive flux? That you should know. Right? It's not clear how you got that, but if you know what it is, and this will become clear as we go through this, if you know what it is, it's a very nice and easy way to develop conservation laws. The other more rigorous approach and a little bit more kind of grounded in truth is to just go after Newton's laws and the laws of thermodynamics and conservation of mass and say, okay, I'm going to apply conservation of mass to a fluid. What does that look like? How can I convert, what does the law of conservation of mass say, and how can I convert that to a differential equation? What does Newton's law say, and how can I convert that to a PDE? Because Newton's law is an ODE, right? dmv mu prime, or summation of forces equal ma. And a is the acceleration dv by dt. It's a total derivative. How can you go from that to a partial differential equation? Right, we're going to untangle that mystery. So this is a little bit more rigorous, in my opinion, but this does a great job as well, and both will lead to the same set of equations. So first, we will start with this as kind of just getting you ready for what's going to come next. So we will start with this approach first, but then once we're done with this chapter and I teach you how to solve these equations numerically in Python. You can see like nice, beautiful plots and animations. Then the final chapter will be on applying these laws to a fluid flow, and we will do fluid mechanics, essentially, advanced fluid mechanics. But first, what is conservation? Not like talking about zoos and the conservation of, species conservation. Talk about like material information. What is conservation? What do you think it is? Okay, but how can you express that in math? What else? What do you think about conservation? Yeah. Anything changing in time is 0. Okay, Isaac, I want to hear what you have to say.
It's like a consistency argument. Like, if I have a certain amount of inputs, I should be able to get a reasonable output. I shouldn't have
something disappearing.
Yeah.
Okay.
I just am missing information.
Okay. Okay. So both of you, so you're all correct. Okay. But what you talked about, what the Isaacs talked about, is Isaac's laws. If your last names were Newton, I would say, okay, so Isaac's laws, you're talking about a different version of conservation, which is more general, and it's called more balance. But what you are talking about, I want you to be more specific. Nothing changes in time, but in what? Like, can I put water in a bucket? Okay, can I have a faucet on the bucket and get the water out? Then the thing will change in time, right? Yeah. The height will change in time. The mass will change in time. So, okay, what condition will you put on the bucket so that we don't lose the liquid from the bucket? Like no faucets, right? What do you call that? So your bucket is the system. Remember your thermal, okay? What condition, what? You said fixed? Sorry, someone? No, not steady state. Pardon me? Closed, okay, so closed, what does a closed system do? No mass. No mass. No mass exchange with the environment. Okay, can it exchange energy? A closed system can exchange energy. Okay, so, but then can we then make that statement about energy? If it can exchange energy, then energy is changing over time. But it can change it can exchange energy. So with his statement is that a quantity is conserved if it does not change over time. All I asked was, okay, but under what conditions? So when we're talking about mass, we said we cannot exchange mass, so the system has to be closed. But we also know that energy is conserved. So what other condition do I have to put on the system? No exchange of energy. No exchange of energy. So what do you call that system when it doesn't exchange mass or energy? Isolated system. Okay? So a closed system is a system that does not exchange mass with the environment. So that's good for conservation of mass. But if we want to talk about conservation of energy, we also require the system to not exchange energy. So we say the system is isolated. And that's truly, very simply, the idea of conservation. So I'll start from laying out some groundwork, and we'll reach this conclusion, this statement that we came up with together. So in all material systems, there is movement of information. Whether you take the system, inside the system there's movement, or there's movement into the system, etc. We're going to work with an arbitrary volume that we design in space. We can go grab some material in this room and put it in a bag and close it, and then seal it somehow so it doesn't exchange energy, doesn't exchange mass, etc. But it can, if we wanted to. But in general, we're going to consider an arbitrary volume in space. We're going to call that a control volume. Why we call it a control, I don't know. It's because the volume we want to control. We cannot control anything in nature except maybe this volume, the size and the shape, right? So we're going to call it a control volume, or CV. Don't conflict that with your resume. So when I say, what's your CV? And you're like, don't send me a PDF, just draw the control volume, okay? And we're going to assume that in this volume, there's an initial total amount of information. Could be mass, could be energy, could be temp, whatever, some information. Okay, there's a total amount of information, okay, that you measure. So if it's mass, and I say, I'm going to collect all the material on this table, just put them in a bag and steal them. What's the mass in this volume? It's the mass of this plus this plus this, so the entire mass of all the materials in this volume. Yeah. Conservation says that for an isolated system that doesn't exchange mass or energy, a quantity is conserved if and only if its total amount does not change over time. Very simply, that's it. Okay? Very simply, a quantity is conserved if its total amount does not change over time in an isolated system. If it changes over time, it means probably your system is not isolated, or the quantity is not conserved. One of those, or both. And remember here, a closed system is one that does not exchange material with the surrounding, but can exchange energy. An isolated system is a closed system that also does not exchange energy. So here are some examples of conserved quantities. Mass, the sum of mass of all components in an isolated system does not change. So if you collect these particles, put them together, material doesn't change, right? And then the statement is that the rate of change of all the masses in the system over time is equal to 0. Doesn't change. Momentum is another one that's conserved, thankfully. And the sum of momentum of all components remains the same. In other words, the sum of m times u, remember momentum is mv, right, or mu. The sum of all momentum, so if you have a bunch of billiard balls, right, if they're like colliding, you can assume a perfect elastic collision, then the momentum is conserved. Whatever momentum the cue ball was contained is going to be passed on to the other one. So for that moment, you have that conservation of momentum principle. Okay, now system might not be isolated, etc., but we can make assumptions there. But it's important to start here, right? Because these are very important to allow us to do something in reality. Total energy is the sum of all energies. Be careful, we're going to talk about total energy because we're going to show later that actually kinetic energy alone is not conserved. The total energy is conserved, okay? Because internal energy, kinetic energy can change to heat, and thermal energy, right? So it's not really conserved. So strictly the meaning of conservation, I know we say it's conserved, it's just changing forms, right? But strictly speaking, the definition of conservation is this. In an isolated system, a conserved quantity does not change in time. If it changes in time, it means it's either not conserved or your system is not isolated or both. Okay, now we'll look at more properties for how to tell whether a quantity is conserved or not. Okay, but not all information is conserved, as I just said. So let's take some examples. Is temperature conserved? Why not? Yeah.
Because different materials, well, like temperature is not, like if you have water and it loses a bunch of heat, then that won't change the surroundings the same temperature as the water was.
Okay.
Only the energy will be conserved there.
Okay. So what you said is really important because that's going to lead us to another point I'll make later. But yes, temperature is not conserved. So if you take a hot ball and a very cold ball and put them in an isolated system, right? So one of them is 100 degrees and the other one is at 10. Well, they're going to exchange heat with each other and they're going to reach some equilibrium temperature based on mass and whatever. But that temperature is not conserved. Now, the equilibrium temperature is conserved, but in general, temperature is not conserved. Because the idea of conservation needs to be for any situation, not only at equilibrium. If they're all at the same temperature and you isolate them, well, yeah, the temperature is not going to change over time. But that's not a conservation statement on temperature. The conservation statement needs to apply for any situation. So if you have two bodies at different temperatures, well, yeah, they're not going to be conserved because their temperature is going to change internally. They're going to reach, like, what are you going to say? Like, their temperature is going to be the average? Well, no, you have to bring in another principle, which is energy conservation, to calculate that average temperature or that equilibrium temperature. And then you still say that that energy is conserved throughout the entire process, okay? Pressure, for example, for the same reason, it's not conserved. It's not a conserved quantity. Kinetic energy actually is not conserved because kinetic energy, it's going to change as the molecules internally inside the isolated system. The molecules are going to collide with each other. They're going to exchange. They're going to hit the wall. There's going to be friction. They're going to lose some of that energy to another form of energy. So there, the total kinetic energy is not conserved. It's changing form, but it's not conserved. So d kinetic energy by dt is not equal to 0. Now the total energy is conserved because the total energy consists of kinetic energy and thermal energy, right? And so they're changing, or you can add potential if you want, right? So they're exchanging forms, right? So then the total is conserved, not individually. All right. So for something to be conserved, going back to Thomas's point, like when you said, it's like you intuitively said, it's not the temperature that's conserved, it's the energy. Why? Because you can count the energy. You can measure it. I give you a very simple example. If I take a system, two systems with the same temperature, the total temperature is not 2 times T1. The total temperature is still T1. Temperature is not, you cannot add temperature. But if I take two systems with two energies, E1 and E2, or E1 and E1, the total energy is going to be 2 times E1 because energy is countable. So for a quantity to be conserved, it needs to be, you need to be able to count it. You need to be able to count it. Okay? So mass can be counted. You can add mass on top of each other. Pressure cannot be counted. Okay? It's not countable. Take two systems with the same pressure, you connect them with each other, they're going to have the same pressure, not 2 times the pressure. Same thing with temperature. So keep this as a guideline. So that immediately rules out temperature quantities like temperature or it's temperature and pressure. But kinetic energy is countable. You can add it, right? But it's not conserved. So not everything that's countable is conserved, but everything that's conserved is countable. Okay? If something is not countable, it's definitely not conserved. Okay, so for something it needs to be countable, we need to be able to count it. Now, information that can be added and counted to each other is called extensive properties. So mass is an extensive property of the system. Momentum is an extensive property. Energy is an extensive property. Quantities that cannot be added are intensive properties. Now, there's a difference between intensive used in engineering and thermodynamics. For what we care about now, take temperature, pressure, density. They are intensive properties. They are not added, right? So you take two materials with the same density, the total density is still the same density. Although density is related to mass, but mass is extensive. So density is the intensive version of mass, which is the extensive property that can be added. So we say conservation of mass, not conservation of density. Okay? And I put this in the statement. For a quantity phi to be conserved, a necessary condition is that it is an extensive property. However, not every extensive property is conserved. Okay? But a quantity that is intensive is definitely not conserved. So temperature, pressure, you immediately figure that out, that they're not conserved. I created a little table here for you to summarize. Mass, momentum, they're conserved. Velocity is not conserved. Okay? Velocity is not conserved. You don't add the velocities of two particles colliding, you add their momentum, right? Because the momentum is going to bring in the mass. If it's like if a bigger car is colliding with a smaller car, it's not their speed that's going to matter and determine what's going to happen after the collision. It's the inertia, where the mass of the bigger vehicle required more energy to move it, right? So then momentum would be conserved. Total energy is conserved. Kinetic energy is not conserved. Temperature is not conserved. Pressure is not conserved. Internal energy is only conserved for inviscid flows. So under certain conditions, we'll talk about that when we hit the energy equation. Now, this puts us at an impasse, and something weird happens here. Like, well, we've been solving the temperature equation, right? How the heck did you get a temperature equation and you're saying temperature is not conserved? Well, for two reasons. You can still develop equations for non-conserved properties. They're just a nightmare to work with, because there's going to be a lot of source terms to account for all the ways that that unconserved property, you have to account where it's going. And oftentimes it's mysterious. Where do you figure that out? A better approach would be sometimes to take a conservation law, so the equation for total energy, for example, and make some assumptions and convert that conservation law into a temperature equation. It doesn't mean temperature is conserved. It's the energy that's conserved, but under certain assumptions, you can convert that energy, because temperature is connected to energy, right? But you have to make certain assumptions so that you can make a statement on relating the total energy into a temperature, right? But you can only do that in certain assumptions, under certain assumptions, right? So you're always going after conserved quantities. The advantage of working with conserved quantities, I mean, there is an equation for kinetic energy in fluid flow. But how do you get it? You get it by multiplying conserved momentum equations, right? To get a kinetic energy equation. But it doesn't mean that the kinetic energy is conserved in this sense that I described. This is the strict formal definition of conservation, okay? But then what happens when you do that, a lot of weird source terms show up in the equation that, like, okay, this is probably accounting for all the ways that kinetic energy is changing and losing and gaining amounts. Okay. Now, it's easier to work with conserved quantities because normally their equations are very simple. There's a rate of change, there's a flux, and there's a simple generation term. They're really straightforward. Okay, so that's why we prefer to work with conserved quantities. Most real systems, however, now this poses an issue, right? Because we said we can only conserve a quantity in an isolated system. But in reality, systems are rarely isolated. Seems like just a pedantic academic exercise. If the system is isolated, I will tell you that your turbine will work. but it's open to the universe, right? There's all sorts of things going on. So realistically, we cannot work with isolated systems. We have to work with open systems where there is exchange of matter and energy at the same time, okay? Now, can we do that? Yeah, we can do that by simply changing the boundary of the volume. So by allowing the boundary of the volume to be transparent, in other words, to exchange information with the surrounding, if we take this concept now and apply it on a conserved quantity, remember, a conserved quantity, you can count it. So you can count how much is coming in and how much is leaving. So there's still an advantage of using a conserved quantity on an open system. It's just not called a conservation law anymore. People will still call it the conservation law. It's not a strict conservation law, okay? We will call it, and I will call it, a balance law. So that's what the Isaacs described. A balance law is whatever's changing inside is accounted for by what's coming in minus or plus what's leaving plus what's being generated, okay? So it's a balance law, but we're going to apply it on conserved quantities because we are for certain that conserved quantities are countable. We can count what's coming in. We know a lot about conservation, and then from that we can develop equations for possibly unconserved quantities. So these would be derived quantities, but we'll stick with conserved quantities. Okay. So in this case, we might still call it conservation law if you want, but I like to call it a balance law or a balance equation. So in the most general sense now, I'm drawing this volume inside a general fluid flow that is moving information around. And that system is open to the fluid. So there's fluid coming in and fluid leaving throughout different ways. Things are happening inside the volume and outside it, right? And exchanging information and stuff. And I'll tell you the balance equation, then give you a 5-minute break, okay? Then, in this case, the balance dictates that the change of total phi in time, phi is still a conserved quantity. So for an isolated system, d phi by dt is 0, okay? But now that I open the system, okay, it's like, okay, the rate of change of total phi in the volume is the stuff leaving minus the stuff entering plus any things that are being generated inside that volume. I'll give you 5 minutes, then we'll talk, and let's resume, guys.
So that's why you
Okay, let's see, what do I have here? Okay. Let's resume. So now we've opened up the isolated system or the control volume to the surroundings. There is matter and energy and information coming through that volume. And the balance expands the conservation law to say that the change in time and total phi is stuff leaving minus stuff entering plus sources minus sinks. Okay? If you forget about sources and sinks for a minute, it's obvious why you add sources and you subtract sinks, because if you're adding stuff, the change in time needs to be positive. If you're removing stuff, the change in time needs to be negative. Same thing, stuff leaving minus stuff entering. Sorry, so it should be stuff entering minus stuff leaving, because stuff entering needs to increase the... How could I do this mistake? You should be fired. Stuff leaving. Okay. So stuff entering minus stuff leaving plus sources minus sinks. Okay. We'll keep it at that because that's going to mess up the diffusive flux, but you'll see the trick there. All right, so we're going to start with this term, the change in time of total phi in the volume. Okay, if total phi, so that's capital phi, that's the total value. So that means simply this is d phi by dt. Okay. Now, as I'm thinking ahead, it's cool to know the total phi in this volume, but what's even cooler is to know what's happening point-wise inside that volume at every point, so I can see like cool, interesting structures. Like I can look at the energy at every point in the system, not just the total energy of the system, right? And so as I think ahead, I want to change this. So if we think that total phi is made up of smaller phis, like maybe per unit volume, then we can write this total phi as the integral of the small phi over the volume. Small phi is therefore stuff per unit volume. So if capital phi is mass, small phi is mass per unit volume, which is density. If capital phi is momentum, m times u, then small phi is m times u over volume, or rho u, right? So all we did here is, as I'm thinking ahead that I want things to be pointwise, this integral is getting me in that direction. Because this integral is going over every point in the volume and adding up. That's why it needs to be an extensive property, because we need to be able to add it, adding up all of the values per unit volume in the volume. It still has the same unit, because this is stuff per unit volume times volume. The final units or dimension is stuff, right? And then per unit time t. OK, good. Here are some examples. Conservation of mass. Capital phi is m. That's the volumetric extensive quantity. Small phi is rho. That's mass per unit volume. Conservation of momentum, mu. Mu is a vector field, remember. Then the small phi is rho u. That's momentum per unit volume. And there are three components of momentum: rho u, rho v, and rho w, as we said about the velocity vector field for a fluid. Conservation of energy, m E0, then the small phi is rho E0. Okay? Not a huge mental challenge here. OK, good. Next, we need to deal with the stuff leaving and entering the system. Okay, this is a little harder. Like, this is probably just the hardest part of all of this. Once you figure this out, you can apply this to any system you want. There are two mechanisms that move macroscopically. Well, as we perceive them in engineering, there are two mechanisms that move stuff in and out of a volume. They can have different forms and formulas, but there's only two categories. And the first one is advection. Advection moves information at the macroscopic visible scale using the fluid velocity. So again, I give you the example. If I have a baked pie here or some incense, you see the incense kind of slowly rising. If I put a fan over here, you can see the incense suddenly move over there. So that concentration of that smell is being transported by the air blowing, by that speed. So that's called advection. Advection, the purpose of advection is to move things from one location to another using velocity. So it's a bulk process. It's a macroscopic process. Okay? You need to have a velocity field or a fluid flow for this to work. Otherwise, you don't have advection. Okay? The next mechanism is called diffusion. It's the movement of information at the microscopic level as perceived macroscopically. Okay? So we know at the molecular level, it's the molecules shaking and like vibrating and like connecting information to each other. I need to pass this concentration to you, and then they're all kind of shaking, like all they, kind of moving erratically, right? But we perceive it as diffusion. It happens. It's different than advection. Whether there is a velocity field or not, it's going to happen. Drop in ink in water. It's still water. You will see that ink slowly form these beautiful structures. There's almost no advection there. There's no fluid motion. It's just the ink diffusing through. You come and mix it, you're going to transport it with the water velocity, right? And you're going to mix it better, right? But that one is diffusion. This one is advection. Now, diffusion also has to be driven by gradients. Higher concentration to lower concentration, higher temperature to lower temperature. If the concentrations are the same, there's no diffusion anymore. If there's no speed, no velocity, there's no advection. If there's no gradients, there's no diffusion. That's why the ink diffuses, because you drop a high concentration of ink in a zero concentration of ink. Okay? On average, the ink is going to spread out. Now, still some more. Advection and diffusion, they bring in and take information out of a volume using the idea of fluxes. Okay, so if you're coming from the sciences, this is probably the first time you hear of a flux, unless you did some physics with fluid flow, but that's okay. I'll define the flux. It's a very easy definition. A flux is simply the rate of movement of a quantity per unit area. Now, rate is per second. Agreed? So the dimensions of a flux is stuff per second per square meter, or stuff per time, per unit time, per unit area. In other words, the flux is stuff per meter squared per second. Okay? Now, I'll give some examples. In general, for any quantity, intensive quantity, small phi, not the big phi, we're bringing in small phi, the advective flux always looks like U times phi. Very simple. It's really simple. You're multiplying, you're moving. It's like, what is advection? It's just velocity times the information per unit volume. The diffusive flux, I will only talk about one type of diffusive flux in this course, and it's the simplest. It's called the Fickian diffusive flux. And it's simply minus a coefficient times the gradient of some function of the stuff that you're transporting. With Professor Sutherland and Professor Yachau, you learn a lot more about different diffusive fluxes, but they're all more or less driven by gradients. Okay? Now, there's a reason I have a negative sign here, okay? Because the gradient points in the direction of high value, but I need motion to move from high to low, so I multiply it by a negative sign. Remember, gradient always points in the direction of the large value. So if I have a high concentration of ink and a small concentration, the gradient is going to be pointing this way. But I want information to move from high to low, so I put a negative sign. I flip it. Okay, that's why you see a negative sign in front of the diffusive flux. But the advective flux, there's no negative sign in front of it. It's just moving with whatever the velocity is moving. Okay, so let's dig into some examples and look at the dimensions. Very important to keep your dimensions and units in check, please. Okay? All right, advective flux, UV. Let's do some examples. Mass advective flux. Remember, for mass, the intensive phi is rho, not m. It's mass per unit volume. So the mass advective flux is U times rho. Now check the dimensions or units. You have kilograms per cubic meter times meter per second. You end up having kilogram per meter squared per second. Mass, rate of mass, kilogram per second per unit area. So that's the flux of mass. That's the mass flux. Mass advective flux, kilogram per meter squared per second. Okay? Remember, we said the flux is stuff per meter squared per second. Momentum advective flux will take x momentum. So x momentum is m times the axial u velocity. The intensive version is rho u. So then, this is really cool, the momentum advective flux is u times rho u. Now u, this is a vector, because think of x momentum as just a momentum quantity. X momentum is going to be transported by the velocity. The velocity is not the same as momentum. It's related, but it's not the same. The velocity can actually advect momentum. Now, if you were to write this rho u, you're going to be like, what u is advecting you and me? And no. It's the velocity field advecting momentum. You have to think about it physically. Although you'll see people write it as, later we will write it as rho u for simplicity. But you have to keep in mind that this is an advective flux. What is being advected? It's momentum. What is advecting it? It's the velocity. Now look at the dimensions here. It's momentum per meter squared per second. What is momentum? Mass times velocity, right? Kilogram dot meter per second per meter squared per second. This is cool, right? We're on to something. Heat advective flux, sorry, I call them convective. I should call them advective. And they're the same, but I want to change the word so they don't call it convective anymore. Okay. Heat advective flux, in this case, we're deriving this from the energy equation. We will do this later. But in this case, what's being advected is this quantity, rho times heat capacity as constant volume times temperature. Okay, this whole quantity is has units of energy times velocity. So energy per unit volume times velocity. That's joule per meter squared per second. So you're advecting energy per meter squared per second. So that's the flux. All of them, stuff per meter squared per second. Now, the diffusive flux, momentum diffusive flux is, again, minus mu, which is the viscosity, dot times the gradient of the velocity. Now, this is x momentum, so I'm only taking the gradient of the x velocity. So this is, excuse me, du by dxi plus du by dyj plus du by dzk. Okay? So 3 components. It's a vector. But the dimensions is still momentum kilogram per meter per second per meter squared per second. Same as this one. Advective flux and diffusive flux, they should have the same units, should have the same dimensions. Okay? Heat diffusive flux, so that's what you saw in your heat equation. We had K del squared T, but that was really, as we were going to derive, it's divergence of K grad T. So this is the flux, the heat diffusive flux. It's minus K grad T. Again, grad T points in the higher temperature, but we want the flux to move from high temperature to low, so multiply by a negative sign. It's, again, units of energy per meter squared per second. They're all fluxes. A flux is a rate per unit area. Rate, joule per, rate of stuff per unit area. Stuff here is energy, so energy per second is the rate per unit area meter squared. Good? Great. Okay. Now, in general, you'll have these 2 fluxes, right? Because we said stuff is moving in and out by both advection and diffusion. So both of them coexist. Okay? They don't mess with each other. You know, they coexist, and they happily contribute and take away from a control volume. So in general, your total flux, okay, total flux, which consists of both advective and diffusive flux, we call that J. And it's a vector, man. It's a vector. Okay? It has 3 components because velocity is a vector, the velocity vector field, and the gradient of the scalar or whatever is also a vector. Okay? So the total flux is a vector. It comes in and leaves from all directions. Right? So keep that in mind. It consists of J1i, J2j plus J3k if you want. And it's the flux capacitor. Right? Let's remember that. Have you seen this movie? Okay, good, good. I'm still relevant. Okay. Okay. Now, the advective flux is, like I said, in general, U times phi, and then the diffusive, the fiction, the Fickian, not the fiction, stupid autocorrect. Fickian, it still does it. Okay. Fickian diffusive flux. So Steve Jobs thinks he's right. So he wants to fix everything I write. Okay, so in general, the diffusive flux for some conserved quantity, well, intensive version of the conserved quantity small phi, it's minus K grad phi, and it's a vector, right? And you add those together, you get the total flux. Okay. All right, so we're not done. We talked only about how information comes in and leaves. But now we need to account for the total. Because we wanna equate that. Remember, we said d by dt of total phi is equal stuff entering minus stuff leaving, right? So we need to figure that out. It's about the total amount that's coming in and that's leaving. We don't have total amounts because we have stuff per unit area, okay? So to go from a flux, which is rate per unit area, we need to go to a rate, right? Because the equation was a rate, d phi by dt, that's a rate, stuff per second. So the flux needs to also be stuff per second, or the net stuff coming in needs to be stuff per second. Right now, the flux is stuff per second per meter squared. So how do we get rid of the meter squared? We need to multiply by an area. And that makes sense, because the flux is coming per unit area. But if you add it up over the entire area, surface area of the volume, you're going to get what? The total rate that's coming in from either advection or diffusion. And so, in general, when you define a surface, in this case it's going to be the surface of our control volume, that entire surface, only then can you define the net rate that's coming in through the flux. So, and that is, in general, the integral of your flux dotted, this is where the unit area comes in handy, dotted with the unit area, with the unit normal, right, times the small area. So if you have a total surface over the volume, your flux at every point is going to change, right? It's not going to be constant. Only in limited cases it's going to be constant. But in real cases, your flux from advection and diffusion is going to vary significantly across the entire surface of the volume. So you need to add all of those contributions, okay? Now what this does, the dot unit area, unit normal, it tells you, is the flux coming in or leaving? Right? Yeah, it depends. No, it could be either. So the unit normal is always pointing out. But if J is coming in, then it's going to be entering, it's going to be negative. And if it's leaving, it's going to be positive. But both cases are going to occur, okay? And then just look at the dimensions of this quantity. So we said J is dimensions of phi, okay, per meter squared per second, times meter squared, because this is unit area, right? Then you get dimensions of phi per second, which is the rate, which is what we're looking for, okay? Which is what we're looking for. This should be capital phi, actually. So I'll fix that. Okay, let me fix it right now, so I don't forget. Dimensions of phi, dimensions of phi. Okay. So the dot product with the unit normal is very important, because that determines if things are coming in or leaving. If all your flux, so suppose you have a volume and all the flux is parallel to the surface of the volume, nothing is going to come in and nothing is going to leave, right? Because then they're going to be perpendicular. As we learned, the dot product, when they're perpendicular, is 0, right? So in practice, yeah, you need to sum up all of those, J dot n times the small area. So imagine your surface area is split into small little areas, and you have a flux and the unit normal in blue over here, and you have a flux. In this case, it's all coming out. You have to dot it to determine how much is coming out in that direction or how much is going in that direction. Okay. So far we have d of the integral of phi dv, and then for stuff leaving and entering, it's the integral of j dot n ds. Now to combine them together, okay, I have to put this. Okay? I take d phi by dt equal minus integral j dot n ds. So where the heck did that negative sign come from? Yes, Parker. Yeah. Isaac? You're going to say the same? Good. Okay, so take these two situations. If everything is going in, then j dot n is negative, because the unit normal is always out. They're in opposite direction. But if stuff coming in, I need to have the rate positive. We said if stuff is coming in is negative, so I need to multiply by a negative sign to make it positive. So that d phi by dt is actually growing, because stuff is coming in. If stuff is leaving, then j dot n is what? Positive, because they're aligned in the same direction. Agreed? And in that case, if stuff is leaving, d phi by dt should be going down. Okay? Whoever invented the outward unit normal should have invented the inward unit normal and then just be done with this sign convention. Right? It's just a convention, okay? It's just a convention. So that's why I messed up earlier when I said stuff leaving minus stuff entering, right? Because stuff entering is negative, and stuff leaving is positive, right? And so I messed that up. Okay, so the negative sign does this, etc., etc. And then finally, we can have a source term. And a source term, it is generated inside the volume, not along the surface. Nothing happens at the surface except the fluxes. So if you have a source term, it's usually generated volumetrically throughout the entire volume. Even if it touches the surface, it's a volumetric effect. Okay? So simply say this is the integral of some source term dv. Okay? And now finally, we have our balance law for a conserved quantity in an open system. Okay? d by dt of the integral of phi dv equal minus the surface integral of the total flux advective diffusive dot nds plus the integral of the surface of any source terms. Okay. This is a super useful equation. It's getting us in the right direction. It's still in integral form, but it's very effective at solving problems. I call this is the undergraduate approach. You can apply this to look at mass and momentum conservation, but you're looking at a total system entirely, not what's happening inside it yet. We're not there yet. You're looking at the net effect, the total phi in the volume, the total flux across the surface, right? The total volumetric effect, not point-wise what's happening. I'm more interested in what's happening point-wise. So if you bear with me, I'll do this, and then I'll let you go. So the integral form is really effective at looking at an entire system. So I call this the undergraduate approach. So I don't know if when you were looking at mass conservation in a system, or like the case where we did the mass conservation in the lakes, we don't look at what's happening inside the lake, the water, as it's moving from one lake to another. We just look at total flow rate out of lake 1 into lake 2, right? And did that balance. So okay, that's good, but if you want to know what's happening inside, you need to do something more. It's much more interesting to look at the interior points. And to do that, we need a differential form of these equations. Luckily, this is within striking distance. I'm going to take this first. It's still our equation. It's a balance. It's a total accumulation. Let's say it this way. Whatever is being accumulated here is equal to, let's say, what's entering minus what's leaving in absolute value, okay? Plus any sources generated, okay? Now the sources could be positive or negative, sources or sinks. It's just that one term, okay? Now if the volume in this region of space is fixed, it's not deforming or moving, which is the majority of cases as well. We have a formula for when it's deforming, but in general, you just pick a fixed region in space. So think of it this way: you're looking at flow in a pipe. You just put your camera on one region and just watch what's happening in that region. That region is fixed. That's your control volume. Okay? So if that region of space is fixed, then that volume is not changing in time. Okay? So what I can do is bring in the time derivative inside the integral. Okay? So I'm no longer integrating in time the total. If the volume is fixed and not changing, if v is not v of time, then this can commute with the integral, and I can move it inside here. So it becomes the integral of the rate of change of phi in the fixed volume. Okay, so now we're headed towards differential equations. Okay, good. Okay, what are we going to do with this? Do you remember? Open up your notes. We did some integral theorems, right? Can you connect this to one of the integral theorems? Okay, what is it? I'm gonna let others take a chance. Look up your notes. What can you say about this? So okay, so this integral is a volume integral. The last one is a volume integral. There's this annoying thing, it's a surface integral. Okay, if it's a volume integral, can we do something with it? Maybe. Let's make it a volume integral. What can you say about that? Integral theorems. It's going to be on your exam so bad. So look at your notes, guys. Just go back on your notes. What happens? All PhD students participate by year 5 of their PhD. They're like, okay, now we can participate. I know you know the answer, but you've answered a lot. Okay. You, Isaac, and Thomas. Yes? The gradient, or what's the other theorem? Yes, so the divergence theorem. So what did the divergence theorem say? That the integral of the flux across the surface is equal, the surface integral of the flux is equal to the volume integral of the divergence. Okay? So make sure you know how to use that very well. Okay? So this integral, using the divergence theorem, you can convert it into a volume integral. This is what's happening along the surface. This is what's happening inside the volume. I am interested in what's happening inside the volume. So yes, I want to convert it into a volume integral. And the last one remains the same. Now everything is apples with apples under a volume integral. I can combine them together. I'm going to move them all to the left-hand side. Okay, so now I have an integral of, oh, look what happened. Integral partial phi by partial t plus div j minus s. Okay, but there's this still annoying integral. What can I do next? You know what I'm getting. This is all equal to 0, by the way. Right? So what can we say about the integrand? Okay, I'm telling you that this is a balance law, conservation law, let's call it. This integral on phi, this integral of whatever the terms are in there, is equal to 0 for any volume. Did I say anything about the volume? Did I tell you that the volume used to be a sphere, a rectangle, a cube? No. I didn't say anything about the volume. It's any volume. So if it's true for any volume, if this integral is equal to 0 for any volume, the only logical conclusion is for the integrand to be 0 for any volume. That's the only logical conclusion. If I give you an integral of f of x, it's valid for any domain, for any bounds on the integral. You're going to say, well, the only logical conclusion is that f of x is 0. If the integral of f of x is 0 for any bounds, the only conclusion is that f of x is 0. So the only conclusion here is that this combination of differential terms is 0. And look at that. Lo and behold, this is our general differential equation for conservation laws. Okay, so we're done. We'll continue on Thursday. We'll apply this to mass, momentum, energy. You'll see all of them have this generic simple form. Okay, you need to know this by heart. You need to understand it and derive it from scratch. And trust me, next semester is not going to be easy if you don't know how to do this. Okay, it took us one lecture to do it. You need to work out the math by yourself. Unfortunately, I'm teaching this on slides. You don't have to take notes. If I were teaching this on the board, it would take me 3 lectures to cover this. You have to write each and every term yourself. I rely on you to do that. You have to write each and every term and ask, oh, is this a vector? Is this divergence? Is this gradient? Is this dot product? What is the? You have to do all of those. Otherwise, you will not learn them. Okay? So we'll leave here. We'll continue on Thursday. We'll apply this to a few different things, and then we'll start looking at solving it numerically in Python. Okay? Thank you. Godspeed.